Hi, my name is Amelia. This is Brandon and Carrie. We're doing our presentation on Loudspeaker and analyzing its as a vibrational system. So the contents of this, we have our objectives, how Loudspeaker works, vibrational analysis, concepts and methods, modeling procedures, the equation of motion, results analysis, conclusion, and our references. So the objective of this presentation is to derive an equation of motion for the speaker from a free body diagram and analyze how the system vibrates and why it's important to analyze its vibration. So a little bit how it works. The figure demonstrates a simplified version of a loudspeaker. The permanent magnet at the bottom of the speaker sits below the voice coil. So when the voice coil has current passing through it, it acts as a magnet, which then changes the, so when you change the current direction, it either attracts to the magnet or moves away from it, causing the voice coil to move up and down. The spider keeps the voice coil centered, but doesn't restrict the coil's vertical movement. So when the coil moves, so too does the cone. So the cone is what's responsible for the sound. It pushes the air molecules. The more the cone moves, the louder the sound produced. The speaker is a good representation of a vibrational system since it has a visible output.
Vibrational analysis is the process of measuring the vibration levels, patterns, and frequencies of a device to detect any abnormal vibrations. Vibrations that can affect the overall condition and function of a device, which may cause future issues or failures. Finding and fixing these issues early in the design phase has the potential of increasing a product's overall quality. Doing a vibrational analysis can increase the ability to find and use the lowest cost parts that can handle the vibrational abuse while ensuring the quality and longevity of the product are built as designed. Anytime a piece of machinery is running, it creates vibrations. This being especially true with the loudspeaker, as its purpose is to produce sound waves by vibrating the speaker's diaphragm. Doing a vibration analysis on a speaker can identify mechanical and electrical faults that can occur within the speaker. This vibrational analysis can be used to check the quality of the materials used and ensuring they will hold up to the abuse of quick repetitive movement while in use over several years or decades, while ensuring the normal vibrations of the speaker do not weaken or loosen any of its components. This will ensure the sound produced will be of high quality for the relative cost of the speaker. Next.
The concepts and methods we learned in vibration theory, we can say a loudspeaker is a mass spring dampening system. The diaphragm, voice coil, surround sound, and spider make up the mass of the system, while the spring dampening element depends on the material properties of the component as shown in the next slides. The suspension can be modeled as a spring element and loss of the suspension can be modeled as a dampening as shown. Vibration has many benefits, such as when we listen to a stereo music, or when it comes to vibrating, these concepts are not limited to the applications of speaker equipment, but also apply to various daily life applications. A speaker is a device used for sound reproduction in which electrical energy is converted into mechanical energy. In a loudspeaker device, the part that converts the electrical energy into mechanical energy is called the motor, known as the voice coil. And the motor, using the vibrational concepts as the motor vibrates a diaphragm that resulting in vibrating the air in the immediate contact with it. Vibration is also used to generate sound waves corresponding to the pattern of the original voice of musical signals. The system will be broken down into three components. The mass spring dampener components, having 1 degree of freedom, which is finite number of degrees, making it a discrete system. It is a system subjected to external force, such as the power supply, which forces the system to vibrate, making it a forced vibration system. Also losing energy from the resistance during the oscillation due to mechanical and electrical dampening. mechanical dampening due to the loudspeaker suspension and the air load of the diaphragm, and the electrical dampening due to the resistant load from the cable resistance and the amplifier output independence. This eventually, in turn, will enable the use of the equation of motion to compare the velocity of the system to its frequency.
Here, the right figure was used to model a loudspeaker as seen on the left. It shows the equivalent mass of the system as being the cone or diaphragm, voice coil, surround, dust cap, and spider. While the spring constant K and damping constant C each vary depending on the material properties used for the diaphragm, surround, and spider. Next.
Theory and procedures. The modeling procedure. The most common class of the loudspeaker is a pistosonic loudspeaker. It is a voice coil loudspeaker, referring to the motion of the driver cone in response to the audio signal from the driver voice coil. A cross-sectional graphic was just shown in the previous slide of the traditional pistosonic loudspeaker is shown prior. As the frequency grows, the mechanical resistance increases, powering the coil by the constant force, and the constant acceleration will cause the velocity to reduce at the same rate as the resistance increases, resulting in constant power. This is shown with Newton's second law, force equals mass acceleration. First, consider the free vibration of the undamped system shown in the equation below. Newton's equation is written with m for mass, the force m x double dot exerted by the mass of the spring is equal and opposite to the force k constant x applied to the spring of the mass equals 0. A traditional loudspeaker is equipped with a suspension, which is normally designed by both a surround attached to the outer edge of the diaphragm and a spire attached to the voice coil. The purpose of the suspension is to center to adjust the voice coil in the air gap and allow the diaphragm to perform the required axial movement while avoiding lateral movement or swaying. The stiffness of the surround along with the shifting mass determines the resonance frequency of the loudspeaker of the extrusion of the cone. It is a single degree of freedom model of the loudspeaker. The free body diagram mentioned by Brandon earlier. Assembled consists of a mass M connected by the parallel following by the dampener defined by its viscous dampening coefficient C, and an elasticity spring defined by the stiffness K. The mechanical system shown as a mass spring dampener system with X as the direction of motion.
To solve for the equation of motion, this figure was used. The free body diagram showing the forces that act on the system as being mass, gravity, applied force, spring force, and the damping force. By selecting the equilibrium as a reference, mass times gravity was ignored in the derivation of the equation of motion. Using the remaining forces and applying Newton's second law of motion, the equation of motion was then derived. Next. Here, the derivation process can be seen as to how the forces were summed and applied in order to arrive at the equation of motion. The equation being a force at a function of time equal to mass times acceleration plus damping times velocity plus spring stiffness times displacement. Next. These are the equations that were used to solve for each variable in the equation of motion to find force, with the acceleration of the speaker cone found as the change in velocity over the change in time, the damping force occurring when energy is removed from the system, where the majority of the energy loss is coming from the speaker's cone having to push the air in front of it, making the viscosity of the air and the surface area of the speaker cone playing a large factor. This divided by the height of the cone gives the greatest damping effect on the system. Velocity was found with the change in motion of the cone over the change in time that it takes to travel that distance. Spring stiffness found using the natural frequency squared multiplied by mass, and the displacement of the speaker cone found at a given time. Next.
So this figure shows how a speaker cone will vibrate after being displaced its max displacement of 0.025 meters and released until it stops. This graph was produced using a mass of 1 kilogram. The speaker takes about 3 seconds to come to a complete stop. So in this figure, it shows the displacement of the speaker's cone with a mass of 0.5 kilograms, half the mass used in the previous figure. The vibration of this system dissipates almost twice as fast as the previous figure. So the calculations used in this analysis were based off of a 10-inch speaker. The system was treated as a simple mass spring damper system. The data's results show the vibrational behavior of the system as an underdamped response. Showing the displacement of a speaker over time represents the vibration of the system since it outputs the maximum displacement of the speaker and the time it takes to displace to zero. Lowering the mass of the system shortens the overall time it takes for the system to reach zero. For a speaker, this is a good representation of vibration. Since there are multiple frequency inputs into a speaker, it is ideal for a speaker to reach zero again as fast as possible to decrease the risk of resonance. Resonance isn't ideal for a speaker since it decreases the accuracy of the sound produced.
Conclusion. This report modeled a loudspeaker, which was broken down into a single degree of freedom, representing the speaker as a mass spring and dampener system, the equation of motion for the system as a second-order differential equation. Deriving the equation of motion by drawing a free body diagram and using a dynamical approach to derive the equation. The solving of the equation of motion after finding the values of mass, spring, stiffness, dampening, acceleration, velocity, and position. After establishing the equation of motion, the complete modeling and analysis of the system at different variables. This report helps to make progress towards the understanding of a loudspeaker. It shows that there are developing reliable models for displacement and current varying nonlinearity in the motor and suspension systems. The knowledge gained from this report gives new insight into accurate measurements and shows how to make measurements more comprehensive, time effective, and critical, and easier to interpret. The DC displacement is a very informative symptom. It gives the unique clues to identify the cause and to estimate asymmetry of motor and suspension nonlinearities. References used are shown.